So it's my pleasure to present you a part of the work that has been done by Cainã BEMFICA during his postdoctorate at CEA, with the close collaboration with our colleagues from EDF and Framatome, Jean-Philippe, MATHIEU, and Pierre, JOLY, and other colleagues also from these companies that help providing the materials and performing the experimental mechanical tests. So the industrial context, the same as the previous presentation, is to guarantee the absence of a brutal fracture of the large components of the primary circuit of nuclear power plants, such as the pressurizer, the steam generators, and most of all the reactor pressure vessels. All these large components are made of low alloy, quench and tempered Bainitic steels. These steels experience ductile to brittle fracture toughness transition, referenced by its reference transition temperature, as you can see on the green curve here. And as for the material of the reactor pressure vessels, this transition temperature shifts towards larger temperature as years go by because of irradiation and retirement, reducing thus the margin that you have in design. If you imagine that you have a pressurized thermal shocks, for instance, you have the margin between the crack resistance here and the loading here. So, but in this talk, we are going to focus more on what can affect the initial transition temperature. And basically, it's due to the modifications of the microstructure of the material. This modification can come from the chemical composition. Because of the size of the components, you have you have differences in the chemical composition depending on whether you are in the components. And you have also an effect of difference in the quenching rates and tempering parameters. Also, again, depending on whether you are inside the thickness of the thick component or in the skin, you don't have the same value of quenching parameter speed, for instance. If you're interested in these issues, I encourage you to follow the presentation of Julie Papin tomorrow at 5:45 in hall 4. Sorry, she will talk about this matter explicitly, the link between quenching rates and temperature parameter with microstructure and fracture toughness. In my talk, I will just focus on an example of the influence of manufacturing routes on the microstructure and fracture toughness of three materials that have basically the same chemical composition. So here are the three materials. As you can see on the picture at the top, they have more or less exactly the same chemical composition, but we have two model materials, the first one MM and the second one HMM, that have been obtained from small ingots of only 100 kilograms, while the last material, the industrial material, is a part of a very large component that is made from 100 ton or more ingots, so not really the same material. For the MM material, it has followed classical hot forging and then austenitization, quenching, and tempering, while the homogeneous model material has been exposed first to a homogenization heat treatment at 12,000 degrees C for 24 hours, and then a quite classical heat treatment, as you can observe in industrial material. So we have performed some experimental characterization of this material. This tests have been performed at EDF. As you can see, we have potential results here of the three materials at different temperature, and we observe the classical evolution of the yield stress versus temperature. The two model materials have more or less the same yield stress, and the industrial material has a slight slower yield stress. Then, as regards ductile to brittle transition, Sharpie impact toughness tests have been performed, as well as a fracture toughness test again, also in EDF. And as you can see now, the first model material and the industrial material have almost the same behavior. So the red points here and the blue points for Sharpie impact toughness or fracture toughness tests, while the homogeneous model material has a much larger transition temperature, but they have, again, the same chemical composition. So you can see that there is a large difference between the three materials, and we try to understand what is the origin of this, and from the microstructural point of view, and how we can integrate these elements into a local approach to brittle fracture model. Okay, so we have started to make some micro hardness maps just to check whether there would be some segregation, chemical segregation on the material that would be revealed by local points of higher values of microhardness. So basically, we didn't find any large segregation area for all the materials. Maybe the first model material has a larger standard deviation, but it's quite okay. They have more or less the same properties in hardness. As regards the crystallographic microstructure, EBSD maps have been performed, and here is plotted the probability density function of missile rotation angles for the three materials. And you can see that you have almost exactly the same curve for the three materials, which is representative of a Bainitic microstructure. But what is interesting here is that the fact that if you define an area inside which you don't have more than 15 degrees missile rotation angle as this area as being a ferritic grain, then you can observe that the homogenized model material has a much larger grain size than the two other one. And this is the key microstructural element that we need to introduce into the modeling. We have performed also a lot of thorough fractographic exam in the brittle domain, both in Sharpie and CT specimens for the HMM material and IM material. And almost each time, we always found only cleavage initiation and propagation, no major intergranular fracture surfaces. And the initiation of cleavage was always, quasi always on the grain boundaries. Sometimes we couldn't find, like this example, we couldn't find any specific particles that initiated the cleavage fracture. But in a lot of cases, we could find some very small carbides that have been enriched in manganese and molybdenum. And in only one case, we could find a cleavage initiation from an inclusion inside the grain. If we sum up all these results of fractographic exams, we can say that in the vast majority of cases, cleavage initiates from grain boundaries. And when we find precipitates, these precipitates are carbides. And only one case, we could start cleavage from an inclusion. So for the rest of the talk, we will consider that cleavage initiates from carbides. So we have studied the population of the carbides for the three materials. And we can see for these three materials that they have very similar populations. The number of carbide per surface area is almost the same for the three materials, as well as the distribution of carbide sizes that we can describe by a livable distribution. And for the three materials, we have something which is very close in all cases. So now let's put this on local approach to brittle fracture modeling. So the key elements of this modeling is to consider first that crack. Oh, yeah, thank you. That crack initiates from carbides as soon as we have plastic deformation of the matrix. And once this happens, the initial size of the crack is equal to the size of the carbides from which it has initiated. So once you have a crack, the probability for this crack to propagate is given by a Griffiths criterion. So the probability for a crack to propagate is the probability to find a crack larger than a critical size. So this is given by the livable distribution I have exposed you before when we were studying by image analysis all the carbide sizes. But here we will just modify a little bit the critical size, which is not just a Griffiths criterion. We use instead a modification of this critical size that takes into account D, which is the ferritic grain size, because we have seen that for the HMM material, this material has a much larger grain size. And this comes from the model of Petch published in 1986 that says roughly that if you have a larger grain size, then you have it's easier to have a longer pileup of dislocation that can help open more easily, even very small cracks that have been initiated on small carbides. So you have to consider smaller carbides for crack propagation. That's why D, if you increase D, you reduce the critical size. So once we can compute the probability of propagation of the size of one carbide, we can compute the survival probability of the reference volume element which says that if you use a weakest link hypothesis, the survival probability of your RVE is the survival probability of all the carbides that are inside your RVE. And then at the macroscopic scale, we can compute again with the weakest link hypothesis. The survival probability of your structure is the survival probability, the product of the survival probability of all your RVE that have been exposed to plastic deformation. That's why we use a VP here. So this model is used as a post-treatment of finite element elastoplastic simulation of CT tests. So we use this type of meshing, and the mechanical behavior is that we use for this simulation is identified on the tension test of each material, the MM, HMM, and IM, at each temperature of the fracture toughness test. And once we have done this, for each time step of the simulation, we can extract the plastic strain fields and the stress fields, and we can compute the fracture probability for a given value of kg. And we can observe this type of curve for different temperature for one material. Finally, the results of the model. So in the points, you have the experimental results for MM material, HMM, and IM. And the curves are the either probability solution of your model. And what you can see is that if you use the correct mechanical behavior, the correct distribution of carbides, and the correct average grain size of each material, you can describe all the experimental results with only one constant value of the energy creation parameter, which is the last free parameter of the model. So we have only one parameter that is kept constant. And basically, this means that your crystallographic microstructure has the same crack-resistant property. And if you do this with only one constant parameter, you can describe the experimental results that were quite different from one material to another. Okay, and so I skip now to the conclusion and just to sum up of what I've said, but if you have questions, I will be happy to answer if I can.